Okay, I'm going to talk about that's the topic. This is joint work with two students of mine, and Finn. So I'm going to talk about dislocations, and the mechanics and physics of dislocations is what my main interest is. I mean, suddenly time flies, and it looks like I spend my life fiddling around with this. But okay, so. But today's talk, we only have a limited amount of time. I'm not going to focus on the mechanics and physics of dislocation. Right? The name of the workshop is Variational Methods, and actually, for the longest time, this is also quite somewhat ironic for me, or personally. I never felt that whatever I did, the models that I had, fit into a variational scheme in any natural way. They were PDEs. That's how the thing came out, and not in any typical variational structure. But that might have changed recently. So that's the story I want to be able to tell you. So Philip introduced Berger's vectors to you. I'm not going to get into the details. So there are so dislocations. For you, for today's purpose, for my talk, it will suffice for you to think that dislocations are curves. They can run from boundary to boundary, or they can end in the boundary to boundary, or they have to be closed loops. And from the pictures Philip showed, and even otherwise, wherever you have the dislocation curve, the lattice is messed up, and hence stresses are produced. And in 2D, these are 1 over R decay. So, more or less, this is at the core, something will happen, it gets regularized, but it's 1 over R. So, and these dislocations, what you need to keep in mind, I'm interested in dynamics, these things move because of the stresses they see. And so each one is producing stress, this guy is seeing this guy's stress, so it's all so all of them are moving that way, and you're applying loads, and this is ultimately a nonlinear elastic crystal, so this is what you got to solve. Okay? So if you just keep this much in mind, that will suffice for more or less a modeling idea that we want to be talking about curves. These curves move. That's what produces plastic deformation of the sort that you see here without the material falling apart. So tons and tons of dislocations are moving. They interact according to the stresses and to the loads. And those lines, this is the micrograph of a dislocation loop. Here, they pattern. Okay, so there the lines are going through in the second picture through the plane of the paper, and under fatigue loading, which is cyclic loading, these lines, there are tremendous densities here and not so much here, and they pattern like this. These are pictures. So they do interesting things, and we want to be able to have a model which talks about these things. Okay. So I'll march right on to the model, and my talk will not even. I want to understand something about how to solve these things, and I'll move on to simpler equations. But this is the model where I want to apply things. Okay. So Philip introduced many things. One picture you want to, one place where. What I'm going to show you, this is the microscopic model where you're thinking of resolving all dislocations. And this is very much predicated on the fact that if you think that you have a bunch of atoms, the bunch of atoms is, after all, the dislocations are configurations within a huge bunch of atoms, okay? And if I am here, I have the bunch of atoms. This bunch of atoms is going to deform and dislocations will move. You're putting loads on it. All of this is going to happen on this bunch of atoms. And to do whatever it needs to do, it does not need to know where it came from, this bunch of atoms. It's all from the here and now. So this is part of what I talk about. There is no reference configuration. It does not figure in figuring out any of the physics. I believe this is important for me in the physical theme. So this is all of this is written in the Eulerian setting. So this is balance of mass, linear momentum. This is the stress. this statement over here, so think of W as an inverse elastic distortion, okay? So you have a lattice and this, okay, so everything is from the here and now, but somehow atoms know where elastically there's a reference for them. So locally, you take a triad and you separate it from the rest of the material, it will go to the unstretched state. That's called the elasticity. So this is the inverse elastic distortion. Think of it as in the deformed state, you have a triad and you cut everything out, this thing relaxes to something, and it's the mapping that takes you from the deformed to the undeformed. That's the inverse elastic distortion. If this were elasticity, this fellow is, so my slides will have equations, blah, 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 right? Don't focus on that. This is just a curve. So, yeah, it is, I mean, okay, so this is the curl. The curl is non-zero. If it were elasticity, it would be zero. Because every curve under deformation has to map to a closed curve. When you have a dislocation, as we just saw, a closed curve opens up. So this means that the curl is non-zero. This is called the dislocation density. So this is that equation, saying that I have dislocations in the material. And this statement is a statement corresponding, it comes from the topological charge conservation. Okay, so there is an equation to sort out here. I'm not going to show you all that. That's not my interest today. It's an interesting equation, but what this says, and this is, I'm not making this up. Okay, so what this is doing is, this is, see, the v, little v is the velocity of the material of the atoms. Capital V here is the velocity of the dislocation lines. The dislocation lines move relative to the material. And when they move with the material, that's elastic. It could be dynamic elastic deformation with dislocations. But that's not plasticity. Plasticity is when the dislocation lines move relative to the material. So this capital V is the relative velocity. So it's above and beyond the material velocity. Little v is the velocity of the material. And what this statement is, it says it's the compatibility statement between the evolution of the inverse elastic distortion and the velocity gradient. So Vk, comma j or partial j, that's a velocity gradient on the current configuration. Everything is on the deforming configuration. So it's a compatibility statement between the inverse evolution of the inverse elastic distortion, the velocity gradient, and this is the plastic rate of plastic deformation. This, if you integrate it out, would be Philip's slip trajectories. Okay. And Philip actually does some recent work where this is sort of the plain vanilla writing of stuff in terms of currents of
with more indices. Yeah.
Oh, you start putting indices, they'll show up, right? You just did the clean version. Okay, so this guy and this guy need to be constitutively specified. The game is this. So this is a standard game. Once you have the kinematics, you play in continuum mechanics. Okay? So what you say is the applied power, this is the stress working on the velocity on the boundary, this is the power supplied, minus the rate of change of the kinetic energy, plus the free energy. You say that this has to be non-negative. Okay? And I'm going to adjust my constitutive equation for the V and the stress so that this is guaranteed. And so if you were not loading it, etc., this would be like a gradient flow of the, the driving forces would be the variational derivative of the energy, okay? But here the energy can rise, but because you're putting in power. I'm interested in doing full-blown inertia also, okay? So you take that statement, you put all of this into that, don't worry about any of this. The issue is, T gets specified, this is a constitutive equation for the stress in terms of the free energy, and the velocity, for this velocity you get a driving force. Again, don't worry about the form, but the point is, if you chose the velocity to be in this direction, parallel to this, then you will not be creating power because of in your model. Okay, it will always be dissipated, whatever you supply. This is a microscopic model, and just to convince you, okay, so I'll give you. Okay. Let me give you this slide. So I gave you a complicated model here, and I'm not going to be proving things. I'm doing the model. Then I need to convince you that actually I'm not just moving symbols around. So these are finite deformation calculations of that theory. Okay, this is serious. I mean, you're probably these are the first such calculations in the finite deformation theory. And there are big differences from the small deformation theory. Until now, people would tell you, no difference. I mean, it's the same thing. Yeah? Go away from the core. No. If you plot along the x-axis, yes, errors are 0. Plot along there are other directions. You look at it a little more carefully. 100 Burgers vector from the core, there are 10% differences instead. There are differences if you do the finite deformation theory. These are finite deformation calculations. This is another thing about stress fields of grain boundaries. As you increase the number of dislocation in the boundary to starting to form, you have some large stresses and energies, and then you go to 0. So that's another story. You have dislocations that annihilate. So positives and negatives go to 0. Here, that happens in the model. And this is with inertia. So here what you're doing is you have a pre-strained strip, you launch a dislocation and a finite deformation body in the pre-strained strip. You're saying that, okay, so we've done this in the fully coupled case too, but here you say that the dislocation has prescribed velocity faster than the linear elastic speeds, say, of the body. Well, then the elastic waves, how are the elastic waves going to look? You're going to see Mach cone, and you do. So that, what did I do? Yeah. Okay. So, okay. This is to convince you I'm not moving things just. There are results. I mean, the theory produces stuff. Yes, Steve.
What about the space transition section as well here?
Afterwards, coffee break. Okay. All right. So what's the motivation of my talk? All right. So as I said, I've been fiddling around with this for 20 years and becomes like. The conclusion is, even if you want to do numerics, numerics is not easy. It's not like you just throw some center difference scheme and it works out. No. You pretty much have to get the whole thing right, otherwise it doesn't work. It squares very well with theory. The nonlinear system, it's a mess. And saying that I want solutions to a system of PDE after 20 years, it seems to me is a very complicated, it's a very rigorous, very rigid statement. So I've tried to learn a little bit about because I have some physicist colleagues, you tell them anything, they'll say, oh yeah, we can solve everything, we'll make an action functional and then we'll turn our crank and everything will come up. What action functional? I mean, I don't see they have a system of PDE, then the first thing they'll say is we'll make it a dual. And then they'll hit it, produce a Legendre transform. Everything in sight is non-convex. What Legendre transform? But they'll crank out, then they'll do renormal. It's very interesting. And these are not stupid people, by no means, right? So something is going on, and I wanted to sort that out. So I started reading Kleinert from Berlin. Hagen Kleinert's book, and the gauge theories in condensed matter. So I kind of got the idea of what goes on in the path integral business. His explanation is pretty good. I've tried to read other things too. Okay, so looks like if you can put the game into a path integral formulation, then one thing is, okay, it's a huge calculation, but it is a fact that rigidity is gone. Every trajectory matters. Okay, it'll be weighted by the action functional, and if it's like a huge thing, then it doesn't get weighted much, but you stick in every trajectory, add them up. Okay, it's not that simple, but the adding is a huge thing, right? And especially, mathematicians will completely fall apart because you don't have a measure on infinite dimensional spaces I'm saying even in the finite dimensional approximation of the thing. It's still a big calculation, but maybe something can be done. Okay, so I want to do that for dislocation dynamics. Like that set of equations. If you can put it into an action, then they have lots of neat tricks of renormalization, etc. Good ways of thinking about homogenization too. So maybe something can be done. Question is then, okay, so you want to play that game. I like to play many games. So this is one game I'd like to play. Okay, so then you need a action functional to begin with. Otherwise, no go. So what's going to happen? How does that happen? So, and this is a system with solid dissipation with nonlinear elasticity. Okay? So another motivation is you want to find systematic clues for. So the system I showed you, in very simplified it to a small deformation, this, that, and the other, but they're still complex. You get very nonlinear, non-standard PD. Okay, so for example, this would be one realization from that model, right? After making, there's a ansatz and etc. I simplify it a lot. So suppose lambda is a vector field from say omega to R2. Yeah, think of this as an energy. This is very simplified, but it belongs to that class. It depends on curl lambda and lambda. After playing all this thermodynamic game, this is positive, that is positive. So evolution equation for lambda will come out, vector field, lambda by dt is curl, okay, minus variational derivative of E with lambda. Lots of people will be very happy here, right? You can go to work. With there's two multiplying curl lambdas, right? Because think of it, I mean, this is like, even in the scalar case, if you make this a constant, this is Burgers in Hamilton-Jacobi form up to half, but this is not a scalar problem, it's a vector. It's a system of nonlinear Hamilton-Jacobi equations, go figure now. So, okay, this is the kind of thing that comes out of the model. Okay? And in this exercise, if you can do this action, then there are some unexpected benefits. It turns out that you can write down a variational principle for nonlinear elasticity when the stress, it's for Cauchy elasticity, it doesn't come from an energy. So, I wasn't a believer in variational anything, but I don't know now, I'm getting all mixed up. So, you get this, in space-time for dissipative systems, and enough of this. All right, I showed you this. So, this slide basically summarizes what I have to say. After that, there'll be bells and whistles. I'll do right variations, etc. But this really captures the main idea of what I'm going to talk to you about. So, and it's really simple. The idea is, suppose I ask you, the question is, solve a nonlinear system of algebraic equations. So X is in Rn, A taking Rn to capital N, and all possible combinations, underdetermined, overdetermined, doesn't matter. So one example is for A alpha is there's a matrix linear equation, but not square. And even when it is square, need not be symmetric. Okay, question. So think about it. Matrix is not symmetric. Goal, construct an objective function whose critical points solve the system. So what game can you play? The game is this. That, okay, so you take this guy, and I'm going to use summation over repeated indices. Sorry if you don't like it. But it's cluttered enough. The more sigmas will not help. So, take Lagrange multipliers, multiply this. Good enough. And then I tell you, so basically think of these guys as constraints, but no one has asked you to optimize any objective. So maybe you can play with that somehow, right? Okay, so keep that in mind. These constraints can be nasty, but you multiply by Z alpha scalar, and now you slap on a function h of, I'll call the z's, the Lagrange multipliers, dual variables, and the x's primals, okay? So h you slap on only of the primals. What is the condition on the h? There's a large class you can put, but the condition is that you take a derivative of this guy with respect to x. So that'll be that. Okay? And you say that I'll set that equal to 0, and this equation has to be solvable for x in terms of z. Which means, what does it mean? It means that A can be very nasty, like, not totally non-monotone. And think of A coming from a non-convex, derivative of a non-convex. But you stick in an HL hugely convex. You beat everything out of A, and you do this and say, okay, this is what I'm going to do. I need to H. That is the only condition I have on H. So if that is so what that means is, okay, so you should be able to write down a function x of parameterized by H such that, this equation equals 0 for all z in Rn. All right. So we'll do that. So once you have that, you stick that xh function into this place of the x. So now you have a function only of the dual variables. This looks like a standard game when you do calculus of variation, which I didn't do. I've had to learn a little bit. Rockefeller's book. Right. So this h guy, it's like the objective, but I have a lot of choice in choosing h. That's the game I'm playing. Okay, so that's that. Okay, so now let's look at what is the condition for critical points of SH. So SH by ZB, Z. So I need to do a derivative of this with respect to over here Z. So first guy you do derivative with this, that's that. Now you hold Z fixed d by dx, that times dh by dx, dh by dz. But this by design is 0. That's that requirement over there. So what I have is that dsh by dzb equals this. And if I have a critical point of this function, so I have a z that solves this equals 0, then I have solved this equation. Whether a bar was symmetric or not, none of that matters. All right, good enough. This is the main idea. This is what now I'll thrash out in many different ways. There are some twists which will give me a heart attack, but I recovered from the heart attack. So I'll show you what happens. So it's okay. So if this is Z0 is a critical point of this guy, then you have a solution. If the system has a unique solution, no matter what H you chose, if you can produce a critical point of the dual problem, you'll recover the unique solution of the original guy. And very interestingly, when A alpha has non-unique solutions, then, give me 1 second. If A alpha has non-unique solutions, then you might think of the H as actually acting like a selection criterion for picking up solutions of the A alpha problem. Yes, please.
So this condition there that you have on the right,
Yeah.
does that fix H? I mean,
No.
because up to constants.
This is for all Z. Remember?
Yeah.
I'm just saying that
You're saying if I solve this for dH by dxi.
No, you solve it for X.
Okay,
Solve it
so
for
given X, I can then the dH by dxi are given as whatever the left and minus the right hand side for all Z.
Yes.
Let's say I can find a solution, which I think you're requiring.
Yes.
Is it then true that there's only one such H? It's a bit unclear to me because you have the ds hat by dxi.
Yes.
Or could there be several H that
I
settle
think
for this?
there can be a huge family of H's. In fact, there are examples I can show you where.
No, you can have.
Yeah.
Okay.
Yeah. And that you milk that. This selection criterion business is really useful. In fact, as we learn more, I mean, that's probably the most useful feature of nonlinear elasticity. I'll show you in 1D. Okay, so people ask me, it's not that a lot of people have seen it, but natural question is, okay, how is it different from the least squares method, right? You take the A alpha, square it, say it's 0. Why is this different? Yeah, it is different actually. Look at the optimality of this. If this is that, that's not the same as A alpha of x equals 0. So it's not the least squares guy. Even in the linear setting, when you have a matrix equation, least squares, normal equations are A transpose A, A transpose B, right? So this is even when this fellow does not have a solution, meaning B is not in the column space of A, this guy will always produce a solution, minimum norm. That's what you're trying to do. This fellow, no, because A and A transpose have the same column space. So if AX equals B doesn't have a solution, A transpose Z equals B is not going to have a solution. So these are not the same things at all. Okay, that's out. So now let's start doing PD. Yeah, simple cases. I mean, if what I'm saying has any value, it must work out for some simple situation. Heat equation, first order transport equation, etc. All right, heat equation K is a constant, positive constant, right? So we will play exactly the game that I just told you about. Take this guy, multiply by lambda, so that's that. And for now, to begin with, assume that lambda has compact support in space-time. So it varies in whatever space-time domain you've chosen. So you integrate by parts, that's that. Now you slapped on the h. And now you say that, okay, I'm going to choose an h. You're free to choose, but must be that h prime is monotone. This is, in the linear case, this is like the Legendre transform business, right? So h prime is monotone, so that I prescribe any p, I will be able to recover a function theta of p. Good enough. If I had such a function, then I'll write the Legendre dual. So this is m star. Take that theta p, multiply by p minus h, and stick in the theta p in the function. Right? That's the standard Legendre transform. And based on the structure of this statement over here, call the negative of this minus of p. Call the negative of that p. And then you note that with those substitutions, this statement is exactly negative of m star p. Okay. No matter what h you chose. And then you do the first variation of this. Of course, this by definition will give you m star of p is theta p. So good enough, theta p. And so you do the first variation of that. So that will be the variation of p over here. Lambda has zero compact support, we integrate by parts. You're back to this. This is the heat equation with now theta written in terms of p, and p is in terms of these dual variables. Okay, very good. At this point, you're very happy. At least I was happy. You do a little more of the exercise and say, okay, I'm going to choose. Let me choose the simplest possible h, theta squared, half theta squared. And I told you about the heart attack, that this is when I got the heart attack, right? Because, okay, so this will be the dual Euler-Lagrange, and this is the wrong sign, okay? Because if this were a positive, this is dispersive waves. This is negative as an initial value problem, it's ill-posed, because the growth factors for m is the wave number. There's a plus wave number 2, this is not going anywhere. I mean, this is like the backward heat equation, right? How can when things, life doesn't work out that easily, right? Okay, that's what happened. Question is, can you recover? All right, so you sit and think about it. Either this is complete nonsense or maybe this something can happen. Something can happen. So the idea is, notice, okay, so the heat equation is an evolution equation. It has one derivative in time. Somehow the dual has two derivatives in time and four derivatives in space. Okay, whatever. So, but I told you it cannot be solved as an initial value problem. So you solve it, think about what's the next best thing you can do. Let's say we want to solve it as a boundary value problem in space-time, initial boundary value. Well, boundary value problem in space-time. Okay, boundary value, so what boundary value problems are you going to assign? I have, so for if it's the heat equation I want to solve, there are three conditions, one on this side, one on this side, one in the initial condition from the heat equation. Good enough. Now, very roughly, I noticed this morning that I had this thing turned around. You would think that there are four derivatives, so you can put four derivatives in space, two derivatives in time. There are six conditions that you can impose. The heat equation provides you three. There are three more. And so you would expect that, okay, so maybe I can put a lambda on top. Over here, I'll put some values of lambda. But then you have to ask yourself, okay, I'm going to constrain the dual variable value. The initial value problem in theta cannot have a constraint at time capital T, the final time. So what's going to, can this be worked out? Turns out that, yeah, it will still be fine. Why? Because of the h I chose, theta is just p. P by definition is this. So if I prescribe lambda on top over here, you see this term is fixed. This second derivative in x. But this term is still free. The lambda by dt is allowed to change. And this will adjust to your initial value problem. Very good. So maybe there's still life after this, right? So, and indeed there is. So what you do is, okay, so now this is our, so we like to solve everything in first order form. So you take the heat equation, call the theta dx pi, that's that. Initial condition, on the left there's a Dirichlet, on the right there's a Neumann, and you take the potential to be just this, the h guy, quadratic. The dual to primal mapping, play the game. This is what it comes out to be. Theta comes out to be this, pi comes out to be this. P is the Lagrange multiplier for this equation, L is the Lagrange multiplier for that equation. Okay? And you write the dual variational principle out, so that's that. And all the boundary conditions and initial conditions of the primal problem, they become natural boundary conditions for the dual variational problem. I mean, this is a linear problem. I can do uniqueness for this. So you can figure out all possible combinations of boundary term conditions you can prescribe for uniqueness. So you can prescribe, along with these things, you can prescribe these on the Lagrange multiplier fields at time t, you can prescribe that value. And these are arbitrary. You can prescribe them more or less arbitrarily, okay, to get the right solution for the primal theta problem. The dual Euler-Lagrange for this is that, which by guarantee, like I showed you in the algebraic case, this is really the primal equations with the mapping stuffed into them, okay? Put in theta of that, phi of that into those, that's what you're going to get. And you look at the quadratic form from the principal part, so that's that. Turns out it's degenerate elliptic because, the heat equation has a characteristic. Flat guys, they become the characteristic surfaces. So that's what you get. Okay, it's degenerate elliptic, but you can prove uniqueness for smooth solutions. So good enough. Proof of the pudding. Okay, so this finite element calculation. Okay, of course, this is just. I mean, I'm not suggesting that the heat equation be solved by this crazy method, but it's a good check, right? So that's that. Initial condition, left Dirichlet, Neumann, L is 1 and T is 1, kappa is 0.2, just to be able to see, time plots going that way. These are good solutions, okay? Errors are 0.18%. And if you hack it off over here, it's 0.011%. So you can nail this, no problem. The thing works. Okay, so that's that. All right, so now it's time for connections. So I told you what my motivation was, how I came to this, and then I've been doing this from 2020, the pandemic winter. Okay, so then I realized that actually Brenier is I've come to realize he's the oracle of hidden convexity and everything. So he's done a tremendous amount of work in all kinds of variations. So I'll show you how my stuff is related to that, right? So Brenier has this paper on the Euler equations, and this is Navier-Stokes written a little differently. So this is the incompressibility. You just give a name to the symmetrized velocity gradient, and then you do this. It's sort of a mixed formulation, if you will. And I could write down a dual formulation, a variational principle for Navier-Stokes. And in this, if you take, so with the H, you have tremendous liberty, right? You can play with parameters. So I'm not going to get into this, but if you suppose you wanted to do the case where nu was 0, set A to 0, then you don't need this dual variable. And now for the pressure guy, this AP, if you take to 0, AP is in the denominator, that will impose the divergence precondition on this dual field. And then this, what's left over here is exactly Brenier's Euler equation functional. Okay. Good enough. Of course, then Brenier does some very serious analysis on this. That's beyond me. Okay, so that's one thing. It's a good sign. So then I read more. Brenier has been going at it with a book. He's been trying to write this for 20 years now. So and this is the latest version which I could find from his website. I looked at that. So I want to show you the connection of what I'm saying with what Brenier is doing. Okay. So basically, our scheme fits within Brenier's overall approach, but there is a difference in point of view, and I want to. So Brenier does not. He pretty much forgets about the optimality condition and the basic Euler-Lagrange PDE, right? And maybe for obvious reasons. He wants to do analysis on this too. My whole goal was completely driven by figuring out a situation where you will be able to say something about critical points that solve the original PDE. So that's one. So look at this in the context of the first medium equation. That's that, u squared. Okay, good enough. So what Brenier says is that take u squared, and don't ask me why. But so take u squared, put this in, and phi is his Lagrange multiplier. And you integrate by parts. This would be exactly the integrated by parts, treating this guy as a constraint. Stick in u squared. Then you want to look at the dual problem, so you interchange the sup and the inf. So you go there. Now you do the inf pointwise, and that gives you the mapping. This is exactly that step. And now you take that fellow, and then you look speaking the inf. Now you made the S. Remember, it went from S hat to S. This is that step. Basically, you now put in the mapping into the original guy, and this is what you're going to get. Then he gives these things some names. Q is this, sigma is that. Of course, he's going towards optimal transport, right? That's his theme. He gives that, and this is exactly the optimal transport statement in terms of the dual variables. So there's a connection of all that we're saying, transport. And in terms of the dislocation system, also things will happen like this. So in what I'm saying, it's not necessary that you work with just a u squared. You put in any HU that basically facilitates the pointwise infimum, or rather, I think of it more as a critical point. Just get the extremized thing. So that's that. And after 3 years, you realize all you're doing is really a very glorified change of variables, right? I mean, in a global, stable way. I mean, it's not some local thing. So that dual to primal mapping is the change of variables, which makes the PDE work out. You to make it better. And my stuff is very related to making the point that whatever you do, ultimately that mapping stuck into the primal equations will give you the actual equations. That's the dual Euler-Lagrange, and that's exactly the primal equations with the dual to primal mapping stuck in there. Okay, so I'm not. I got the heart attack, but other people have gotten ulcers about the point that I mentioned. And so that's here. Okay? So look at what Brenier says. This is a busy slide. You don't have to read everything, obviously. I'm going to take you through, I'll try to take you through what he says. It says, it seems foolish to solve the IVP, the initial value problem, by a space-time convex minimization technique. I mean, I think this also has to do with the fact that the least action principle which Brenier worked on, this is That's really a final, I mean, so you're giving an initial value, giving a final value, and you're saying, find me minimizing geodesics. That's different from the initial value problem. Okay, good enough. So he says that. So then he says, indeed, this way, we are very likely to get optimality equations of space-time elliptic type. We already saw what happens. And therefore, ill-posed, although there is a little room left if the convexity is sufficiently degenerate. So Brenier is linking, as I parse it, is linking everything to, you are able to solve the initial value problem because the actual problem is degenerate elliptic. I actually, okay, so you take it for what it's worth. I don't think that's the key issue. Although for all evolution problems, like the heat, and I'll show you the transport simplest ones, the dual problem will be degenerate elliptic. That's a fact. So now what he says is take a first order system of conservation laws. It has an entropy flux pair, and you play the same game. So this is the dual problem now with the entropy put in here. You basically do the Legendre transform. This is what that happens. And this is the final problem. And then he says, he sees a paradox. Here is the paradox. How a convex optimization problem could be compatible with a well-posed evolution problem. Remember, the well-posed evolution problem is in the primal side. So then he goes on to say, for instance, if G were just a square, this is what you'd get, whose Euler-Lagrange would be the backward sort of wave equation. Yeah. And his answer is, the answer to the paradox is that in our construction, G is very likely to be convex degenerate, just convex. And this is what he says, but okay, my feeling is just this, from the example of the heat equation I showed you, and I'll show you a transport equation too. Okay, so this is the dual problem. So solve the A problem as a space-time boundary value problem. Solve the dual problem as a boundary value problem. I don't see a problem even if it were elliptic. It would be even better actually, but it never is, because you get characteristics like in the heat equation, the transport equation, I'll show you. The point is, at least from my point of view, this still leaves enough freedom for the primal variable. The dual you solve as a space-time boundary value problem. I showed you, right? The order increases, so you can still solve the dual as a space-time boundary value problem, but this does not get in the way of your primal being able to evolve properly. I mean, that's what happened in the heat equation. Look at the heat equation example. And my point of view is, if the problem were to be elliptic in space-time for the primal variable, for you, well, this problem somehow you fiddled around and you came up with a formulation and suddenly it looks like an elliptic problem in you, that is a problem. But that is not the case here. The dual guy is a space-time elliptic problem. No. And okay, so simplest possible transport equation, first order wave equation, first order system. So this is a scalar transport C constant, characteristics going this direction, C is greater than 0. On the left there is a boundary condition and initial condition. Okay, quadratic, take the H to be quadratic, exactly quadratic. No, don't have to go looking for problems. So you play them, just run the machine. This is what it comes out. So put these Dirichlet conditions. So again, you can do formal uniqueness, so you know what conditions you might want to put. The dual Euler-Lagrange will be this. You look at quadratic form for this one. Turns out it's degenerate elliptic. It loses ellipticity exactly along the characteristics where it must. And that much you must have. Why? Because you know that the primal problem has so it can be discontinuous across characteristics. See, the U comes out in terms of gradients of the dual field. So the dual problem has to admit, has to have some non-ellipticity in it, because otherwise you can't have, it has to have gradient discontinuities at least. Because otherwise, how can U be discontinuous? Then it all fits. So The initial value problem, that's the, okay, enough said. So it works, and it works even in a computation, yeah. And no, these are no manual intervention. I mean, pretty simple calculations. You do that, and we are doing it with continuous finite element interpolations, so you're not going to get the jumps right. But this is good. I mean, error is all concentrated along the characteristics. Okay. Very good. In my remaining time, how much time do I have? 5 to 10 minutes. 5 to 10 minutes. Okay. So non-convex elastostatics, right? This one. So double well, and you put y minus alpha x squared. Yeah, and y on the left side you hold it fixed. On this side you put alpha star. Good example is alpha 0, alpha star 0. Everyone here knows this better than me, so I don't need to tell you what happens over this. Okay, so for alpha star 0, limit of minimizing sequence is y equals 0, and v is the derivative, v equals 0. That's not a minimizer. Good enough. It's not a minimizer. But look at one thing. I mean, you write down the Euler-Lagrange equations. That definitely is a critical point of the Euler-Lagrange equations. Y equals 0, v equals 0 for alpha equals 0 solves the Euler-Lagrange equation. And this is what we are going to go after. So, okay, very good. We play the game, right? So again, you take, okay, so now one very important thing over here is, until I told you I'll choose the h to be a function of only the primal variables, right? So in this case, it will be y and v. But actually, it turns out the crank goes through if you make h explicitly a function of the independent variables too, x and t, when it's there. So here is where by choosing that dependence on x, we are going to use different h's as a selection criterion. Okay, and you choose the h quadrat, so h is of this form now. H is y minus, this fellow is free to choose. You choose whatever you want. If you get the dual solution, then it's good. And for v0, I take a derivative of that guy, stick that in. Explicitly, you can write out these mappings. So h, yh will be this, vh will be this. Put those guys in there. That's the dual functional. The linearized gradient flow of the primal guy about the solution you want, y equals 0, v equals 0 is ill-posed, obviously. But for the dual guy, it is good. And okay, so some solutions. So what are we going to do? Here we've done all kinds of alpha star combinations. Everything works nicely. So in the examples I'm going to show you, what I'm going to show you is this. Okay, so y equals 0, v equals 0. We are going to choose. So we're going to put it into a Newton scheme. And you're going to choose guesses which are quite far away from the actual solution, the y equals 0, v equals 0 solution. So, for example, the guess is 0.3 in the gradient. So, 1 is the well, 1 and minus 1. It's 0.3 minus 0.3 in the gradient. And you run the dual guy, and boom. So, there's a serious basin of attraction to. And this is the example where, okay, so let me just set the stage here. So and as I said, for alpha star changing, you get all kinds of solutions, we get those. I wanted to check that you can get some of these weird ones too. So you remove the y minus alpha guy part over here, just read the double well with the Dirichlet conditions. And now we'll think of, take the 10, put 10 hats in the domain. Plus minus 1, 10 hats. Good enough. These red guys are the solution. So 1 minus 1, 1 minus 1. And then we are going to take initial guesses which actually modify the dual, the h that I stuck in, the y naught. Basically, that's what parameterizes the initial guess too. You take them of different magnitude. So here it's a 0.3. Here it's a 0.9 in the gradient, and here it's 5. So 1, 5, that far away, right? For A between 0 and 0.3, you get it gets attracted to the y equals 0, v equals 0 solution. 0.9 gets attracted to 1 minus 1. 5 minus 5 gets attracted to 1 minus 1. And this is all, no sweat. These are, you folks know this, right? This is not an easy problem to do. If you did it with the primal, everyone will be crying and going home, right? But this thing is just worked out nicely. So, okay, so to wrap up, I mean, I was talking about dislocation mechanics. So you can play the same game. Yeah. So you want more indices? Okay. Anyway, but these are calculations. So that's a primal, you play the game, blah, blah. Finally, you get the functional. You write down the functional, and with this understanding, and now looks like you can go after it, and there are good connections to Brenier, hidden convexity, optimal transport. So, and those are, even I understand that, there's something to be said for posing problems weakly. So that's a natural way of doing something this complicated, which have no natural, I mean, the primal problem has no natural sort of weak structure, right? You can't move derivatives onto test functions easily because of the nonlinearities. But this game allows you to still pose a variational problem from there. That's that. Okay, that's a summary, but I think I've told you what you can do. So on the linear, the first thing with the path integral will be you have a linear guide. So now even I understand how to do this for the linear problem. We'll calculate correlation functions. If you have a linear theory, they call it the free field theory. So for the free field, we'll be able to calculate 2-point connected correlation. It can be a good statistical interpretation of this. So thank you very much. I need to thank a couple of people. So, I need to acknowledge several useful discussions continuing over the past 3 years with Vladimir Shverak. He's been very helpful with this, and a couple of discussions with Bob Cohn and Felix Otto. So thank you very much for your attention.